Okay, so here are going to be a couple of problems with angular acceleration. So I'd like you to follow along, have your calculators ready, and here we go. Imagine that you have a fan in your room and it has multiple speeds. You have a fan and it's currently on medium and it's going to high speed. It accelerates at 1.2 radians per second for 1.5 seconds. The initial angular velocity is 3.0 radians per second. Question is, what is the final angular velocity? So here's my initial going for the final, and it's accelerating, so it's speeding up, so we should expect this number to be higher than this over here. Okay, so let's take a look at our formulas. We're looking for omega. There's actually a couple formulas with omega, so let's take a look at them. We have omega is equal to delta theta over delta t. Okay, we don't have anything about the radians though for this. We don't know how many revolutions that it's made, so we actually can't use that one. If we look at another formula, we have the velocity is equal to r times omega, and we don't have the radius, we don't have the velocity, so we can't use that one either. So the last formula that we have is going to be, we have alpha is equal to the change in angular velocity over the change in time. We do have this right here in radians per second. It's actually per second squared. So that's my angular acceleration right there. We have my time, which is 1.5 meters, 1.5 seconds, and we have an initial omega. So we have to solve for my omega here. So we're going to multiply both sides by delta t by delta t. So now let's plug in what this is. My change in omega is going to be my final minus the initial is equal to alpha times delta t. We're trying to find the final. We already know the initial. So we're going to add the initial angular velocity to both sides. So my final angular velocity will equal to the angular acceleration times the change in time plus the initial velocity. That sort of makes sense. Let's take a look at this. My final angular velocity will be equal to my initial angular velocity, also accounting for the acceleration and the change in time. So this will be equal to, my alpha is 1.2 radians per second times the time, which is 1.5 seconds. That's squared, sorry, it's alpha, plus the initial, which is going to be 3.0 radians per second. So the seconds squared will cancel with the seconds there, and if we multiply this out, we'll have 1.2 times 1.5 plus 3 equals 4.8. 4.8, my units will be radians per second. Now, does this make sense? Yes, because my initial is 3.0 radians per second and my final is 4.8 radians per second. So here's another problem. Looking at your car tire. So the radius of your car tire is going to be 0.35 meters. Now the actual car is accelerating. So the car accelerates at 2.8 meters per second squared. Question is, what is the alpha? This is a little bit easier one than the last one. So what is this? The car accelerates. This is my linear acceleration. So it's my regular acceleration. I can also call it my tangential acceleration as well. So I'm going to pause. I'd like you to go ahead and attempt to see if you can solve the answer for this one. Okay, hopefully you've come back and we're looking for angular acceleration. There really only is one formula that we have for angular acceleration, and well, there's two. We have this is going to be equal to the radius times the alpha. The acceleration is equal to r times alpha, or there's also alpha is going to be equal to the change in omega over the change in time. So we have the radius, we have the acceleration, we just need to solve for this. So we're not going to be using this one over here. So we're solving for alpha, so we're going to divide both sides by r. So my alpha will equal to my tangential acceleration, which is 2.8 meters per second squared, all over the radius, which is 0.35 meters. Now take a look at the units. The meters cancel with the meters. And what are the units of angular acceleration? It's going to be radians per second squared. So we just use our calculator for this one. We do 2.8 divided by 0.35, and that will give us 8. So we should say it's equal to 8.0. This is two significant digits, so we need it in two significant digits. 8.0. The units are going to be radians per second squared. Okay, the last problem is going to be a centrifuge. Okay, biological device that spins test tubes very, very, very rapidly. Okay, so here we have a centrifuge that's starting off at rest. So a centrifuge at rest. Okay, it's then going to go to 100,000 revolutions per minute in 2 minutes. So it goes to 100,000, it's called RPMs, revolutions per minute, in 2.00 minutes. So 2 minutes it takes top speed, now we're going around at 100,000 revolutions per minute. Okay, so first let's calculate what I have here. Revolutions per minute. 100,000 revolutions per minute. Well, I have time right here on the bottom, and then I have revolutions. This is going to be on the top. Revolutions is the number of times that it's going around. What is this that it's measuring? Do I have a theta? Is this omega? Or is this alpha? The answer is this is omega. So I want to give you a minute because I'd like you to convert this first into the proper units. After you convert it into the proper units, what we're trying to find in this problem is what is the alpha? What is the angular acceleration? So go ahead and see if you can try to find that. First convert this, and then see if you can find the alpha after that. Okay, hopefully you finished this problem, and we're going to go through. So we need to first convert revolutions into radians. 1 revolution is equal to 2 pi radians. My revolutions cancel, but I can't have radians per minute. I need radians per second. So I need to make sure that I have 1 minute is equal to 60 seconds. So when I do that, I have 100,000 times 2 times pi divided by 60. Okay, we're gonna get this in, we have 1.05 times 10 to the 4th. And this is gonna be minutes cancel, minutes cancel. This is gonna be in radians per second. Okay, that's just kind of rounded. But we're not actually trying to find this. If we were, we would leave it just like this. Okay, we're trying to actually find alpha. Okay, alpha, let's look at the formulas for alpha. We have A is equal to R times alpha. We don't have anything about the radius, so we can't do this one. We also have alpha is going to be equal to the change in omega over the change in time. We do have that. Okay, so we're trying to find for this, the alpha. So here's what we're going to do. So it's starting off at rest. So the change in omega is going to be my final minus the initial. So this is actually going to be my final omega. Remember, it starts at rest, so that means my initial omega, my omega 1 is equal to 0.0, not meters, but it's going to be radians per second over the change in time. So my final angular velocity, which is 1.05 times 10 to the 4th radians per second, minus the initial of 0, all over the change in time, which is 2 minutes. We can actually convert this 2 minutes. The 2 minutes would convert into 120 seconds. And this would give me radians per second squared. Those seconds do not cancel each other out. If the seconds here were 1 over seconds, then those would cancel out. So I'm going to take my initial number because I don't want to lose this data, because we're not really trying to solve for the omega, we're trying to solve for the alpha. And I will take that and divide by 120, and that will give me 87.3 when rounded. 87.3, and the units will be radians per second squared. That's it for now.